Thank you.
Dimitri has over 20 years experience in the area of IT, the last 14 of which have been dedicated to the field of information security, and has a long track record of risk analysis, vulnerability assessments, penetration tests, technical security and compliance audits on large corporate infrastructures of international organizations. He currently serves as Managing Director of Encode Middle East in Dubai. He holds an MSc in Information Security from Royal Holloway and is a PCI DSS Qualified Security Assessor.
Thanks. Good afternoon, ladies and gentlemen. I'm Dimitri. For the next 1 hour or so, we are going to take a look at how some cornerstones of banking security, which up until recently were thought to be secure, have been proven not to be secure anymore. We're going to take a look at ways that people have used to make an awful lot of money, and the ways that people will be using for the foreseeable future to continue making some money. There's an implied assumption there that you understood that the attacks that we are going to discuss this afternoon are not theoretical, but they have actually taken place. For my sins, as well as for yours for the next 1 hour, I come from a cryptographic background. So some of the things that we're going to see refer to cryptography, but it's not hardcore cryptography, and it's not the algorithms that we are going to be discussing. It's all about the protocols and the API exposed by the hardware security modules that store the keys and the pins on which the security of banking transactions are based. So for this afternoon's presentation, we are going to very briefly take a look at physical attacks on ATMs, but we are mostly going to concentrate on IT-related attacks for recovering pins and also what may happen to a banking institution if their internal network is compromised. If I was giving this presentation a couple of years ago, I would have asked how many of you work for a bank, and the logical assumption would be that only those people who work for a bank would be able to perform such attacks. This is no longer true. We will see why. Very briefly, a survey amongst the members of the ATM Industry Association asking the question, what do you regard as the most significant technological weakness in the ATM industry? No surprises there. Nearly everybody said security. And that's on the ATM Industry Association side. If you ask the clients themselves, what is it they're looking for when they're conducting electronic transactions over ATMs? First is personal safety and security, and not very far below, financial safety and security. A few months ago, there was an orchestrated attack in the Gulf. An ATM network was penetrated, and both credit and debit cards were compromised. And it was not just from one bank, it was from every bank, and it didn't just affect the residents of that country, it also affected visitors of that country. It was large scale. We will make conjectures on what happened, since there was an official investigation. However, the official results were never published. Well, if we ever see them on WikiLeaks, it won't be me. There is a lot of concern about financial transaction security. The managers of the ATM networks themselves think so. And it all starts becoming even muddier when people start developing automated tools, code, in order to perform these attacks either faster or on a wider scale. And we have started seeing the first malware targeting either ATMs or payment switches, central infrastructural components which aggregate payment transactions. The objective of those attacks is very simple. Recover the client's PINs and the card numbers. So the perpetrators can clone the cards and then they can withdraw money out of the victim's accounts. So very briefly, how does an ATM work? We all use ATMs. This is the classic idea of everybody. Everybody has about an ATM. It's a box, I go there, I put my card, I put my PIN, money comes out. So it is a place that contains money. So effectively there must be some physical attacks, and there are many, many different physical attacks. First of all, attacks targeting the client, card theft, with using card loops, also known as Lebanese loops, although the Lebanese didn't really have to do anything about it. I think it was the country where it was first detected. I don't think the Lebanese had anything to do with it. Skimming devices, we all read about it. Bogus ATMs, you go to the mall, there's an ATM there, you put your card in, you put your PIN, your card never comes out. Or even if it does, it has already captured the magnetic strip and also the PIN. PIN theft via various means. Cash theft, distraction fraud, which according to a recent ATM Industry Association survey, it is the prevailing ATM attack here in Malaysia. So you go to the ATM, you try to take some money out, and most probably when the money come out, somebody bumps into you, he asks, he says, I'm sorry, but by the time, you turn and you look back at the ATM, the money is gone. Fund transfer fraud, and there are also some attacks targeting the bank with transaction reversals. The old ATMs had some sensors at the top and at the bottom of the money presenter, and you could safely take money from the middle, and after 30 seconds, these sensors did not sense any movement on the cash, they would retract the funds, but you had managed to take some money from the middle. These are being slowly phased out. The old ATMs, there are new ATMs now which have individually retractor bins, so if the money goes back, rather than being taken into a central slot, they're individually stored and matched against the client who did the transaction. So if you take money from the middle, then the bank will know who you are. And of course, ATM burglary attacks, where you go with a JCB and you just rip it away. PIN attacks. Now, for the layman, we saw what an ATM looks like. When you take a look at the ATM itself, it contains some more components. Obviously, the front with the screen and the PIN pad and the card slot. There's also a small safe to keep the money. And then, of course, there is an operating system, the vendor application, and a tamper-resistant module, which performs all the cryptographic operations. How does an ATM network work in general? How are we able to travel to a different country and use our credit or debit card to take money out of our account back home? Well, we go to any ATM, an ATM that does not belong to our bank, be that in our country or in a different country. We go there and we put our card and we put our PIN. The PIN gets encrypted on the ATM, and it is sent to the central switch of that particular bank, which, not surprisingly, because it acquires the transaction, is called the acquiring bank. This particular machine here, the ATM processor, it is equipped with a hardware security module, which decrypts our PIN and re-encrypts it with a key shared between that bank and a central switching network, either Visa, MasterCard, or a national one. The reason being, it's not feasible for all the banks to store everybody else's keys. the key management becomes very difficult. So you have a hub and spoke configuration where you have central locations which share keying information with everybody else. So if A wants to talk to B, they have to go through a central location. So your PIN will get decrypted here, re-encrypted in with the key shared with the switching network. The switching network knows how to talk to your issuing bank, the bank that gave you the card. It will encrypt it with the key of this bank. It will send it to the bank. The bank will do the verification of your PIN, and then it will send it. It will send back an OK or a deny, and accordingly, this will be routed all the way to ATM, and the ATM will either give you some money or you will get a rejection. The PINs themselves, they are encrypted using a trivial process. The PIN is formatted in an 8-byte block, and then either DES or triple DES is used to encrypt that. There is a number of internationally recognized formats for PIN encryption. They have to be internationally recognized, and there is a small number of them, so there can be interoperability of the different networks. The PIN block formats range from the simplest, which is the ISO 2 PIN block, which is number 2 for the version, number 4 for the number of PIN digits, then the 4 PIN digits, and then a filler of hexadecimal Fs. Getting slightly more complicated, ISO 1 with this format, the only difference being that rather than a constant value, the values there for the filler are random. To slightly more complicated, ISO 0, when you have the same like ISO 1, but then you exclusively OR this with a second constant which comes from your primary account number. This is the number of your card. To slightly more complicated, and that's the final format, which is ISO version 3. Again, your PIN, the PIN, some random values, and your personal account number, the PAN. Why does this have implications? We will see later on. The ISO 3 is considered the most secure because it binds the PIN with your personal account number, the card number. It diversifies the encrypted PIN blocks. So if two people with different account numbers, with different card numbers, share the same PIN, and it's not difficult to do, there are only 10,000 pins in a 4-digit PIN quantity, then the encrypted PIN block is going to be different. It's going to look different. If you and I share the same PIN, the encrypted PIN block is going to be different because your card number and my card number are different. We combine that with exclusive OR and then we encrypt. So what do we do in order to generate the PIN? We take the primary account number, we take one key which is stored inside the HSM, we call it the PIN master key, we encrypt this, we come up with a hexadecimal value, and because of course there are no hexadecimal digits on the ATM PIN pad, we do something called decimalization, where we convert every decimal character back into, every hexadecimal character back into decimal. So if the result of the encryption is 4FA2, we do a truncation, we just take the 4 first hexadecimal digits, we map those to decimal values. In order to do that, we use some decimalization tables, which all they do is they map hexadecimal digits back to decimal digits. And this is the decimalization table most used. Now, there is an observation to be made here. Some numbers have more than one hexadecimal digits. Some decimal digits have more than one hexadecimal digits mapped onto them. So for example, 0, decimal 0 maps hexadecimal 0, but also maps hexadecimal A. So they're more likely to occur in issued pins. Is this an implication? We will see about this slightly later on. How do we do now pin verification? There are many different ways. There are simple. We take the pin, we decrypt it, and then we check it against the stored pin. Not very safe, because that means that we store somewhere the original pin. There are pin verification values and there are offsets. The pin generation algorithm is extremely simple. You take the data, which is the PAN, you take it through triple des, you get the ciphertext, you do some truncation, you take the first 4 digits, decimalize, and you get the generated pin. Now, for the pin verification value, you take something called the transaction security parameter, which looks extremely like the encrypted pin block that we said before, because you XOR this with the account number. Again, you triple des it, you truncate, you decimalize, and the result, you can store it safely, either on the strip of the card, or you can store it in a database for verification. Where is the security in all this? The key used for the encryption is secret. It lives inside the HSM. Nobody knows it. There's no way to extract it from the HSM. The HSM will never give you back clear text keys. If you want to extract the key and insert it into another HSM, then you will get it in an encrypted format, and then you will insert it into a second HSM. Now, due to the short length of the PVV, it's just 4 characters, yes? Something known from cryptography and from statistics called the birthday paradox comes into play. So multiple TSP, transaction security processing values, or multiple ISO formats result in the same PVV. In practical terms, there are more than 1 pins for each account. On average, around 60% of accounts have more than 1 correct pins associated with them, and slightly less than 1% have got more than 5. Does that mean we can attack? No, it doesn't. We don't know. However, the legal implications of having more than 1 correct pin that verifies against the pin verification block is a completely uncharted legal territory. Offsets. When a bank gives you your card, they send you your PIN in an envelope, which hopefully also gets delivered via courier. And the first thing they tell you is change your PIN. Now, they store the PIN somehow on the server side, but then they ask you to go and change your PIN. That means that wherever you go to change your PIN will have to travel somehow and become known to the bank for further verification purposes. And this is slightly risky. So there is something called an offset. There is the constant PIN, the initial PIN, known as the IPIN. This is the one the bank communicates to you the first time they issue your card. Then they allow you to change. The bank stores the IPIN, and they store something called the offset, which is a binary, either addition or subtraction. Initially, if you never change your PIN, the offset is 0. When you go to change your PIN, what is calculated is the binary addition or subtraction from the initial PIN. So adding the offset, which is the result of this additional subtraction, adding this offset to the initial PIN gives the client PIN. And this is the algorithm that produces that, which I just described. As far as the API is concerned, because these HSMs, they're black boxes. They are tamper-resistant hardware modules. If you try to open it, it will destroy all keys. If you move it it will destroy all keys. I also come from a country which is prone to earthquakes. So the banks learned the hard way that either they have to put the HSMs on springs or they have to suspend them from the ceiling. Because when there is a violent vibration, the entire ATM network goes down because all the keys are destroyed because the hardware security module thinks it's under attack. However, it does need some way to communicate with the outside world. And that way is through a very well-known, documented, and widely available API. This is one of the functions, which is called the PIN verify function. It takes 4 inputs. It takes your card number, a decimalization table, the offset, and the encrypted PIN block that comes from the ATM. And it comes back with a binary result, true or false. This is more or less what it looks internally. You give it the PAN, it knows the PIN generation key here. So it will encrypt your card number with the PIN generation key. It will create the ciphertext. It will take the decimalization table. It will come up with the IPIN. Then it will also take the offset. It will do modulo 10 addition. It will calculate the PIN. It will know what your PIN is inside the HSM. It never goes out. And then, of course, the encrypted PIN block will come in. It will get decrypted, and these two will be compared. And either a yes or a no will come back as a result. Now, before we start taking a look at the PIN attacks, let's see some characteristics. Up until 2 years ago, or a year and a half, these used to be primarily internal attacks. Only people with physical access or programmatic access to the HSM were able to do that. That's no longer the case. Now we have seen PIN attacks as the results of compromise of internal infrastructure components within a bank, or of compromise of payment switches, generic electronic transaction processors which aggregate transactions and they distribute them to the right networks. They require HSM access. All of the PIN attacks require HSM access. There's no way you can do something without an HSM. The ultimate goal is the PIN discovery. They're not time-consuming. It doesn't take a long time. No special knowledge or other hardware requirements. They're vendor-independent. The HSM APIs are standardized. The reason being, the ATM controlling application wants to talk to the HSM. Now, the vendors, they have an interest in standardizing the APIs. Why? Because if I standardize with my biggest competitor, I can go to his clients and say, swap out his box and use mine, it's better, without having to rewrite any code. HSM network security is again not a viable solution because the functions that are exposed and they are needed for the entire operation, for the entire network to work, are made available. So these are the functions that we're trying to compromise. And of course, inactivated pins can also be discovered. If a bank produces pins and cards in a batch mode and does personalization later, you can compromise the cards which have not yet been issued to clients. Personalization will be sent later on. So, we said that all the banks share some kind of crypto material. So they have some communication keys to talk to Visa, to MasterCard, to interbanking networks. Usually, the way these keys are exchanged is they're broken down in different parts, which are being shipped by different couriers to different people who will go at different times to the HSM, put them in, then the HSM will XOR them and create the communication key. And of course, the majority of you, knowing what exclusive OR is If I have just one of the key parts, I have no clue whatsoever what the final key is. It's a one-time pad, provided, of course, it has been generated securely. So, how does it usually happen? We give the HSM one key part, encrypted under a master key, but this is irrelevant. We give it a second part, again encrypted under a master key, but this is irrelevant. And then what the HSM does is it XORs this, and it comes up with the final key. Now, what if an operator is able to perform these two transactions himself, but rather than giving two different key parts, he submits the same key part twice? Since the HSM is going to exclusively OR the two parts, when you exclusive OR a quantity with itself, what do you come up with? 0. Excellent. So what do we have now? We have a known key. We have a key whose value we know, and it's 0. Whatever that key may be, and whatever use we might have for it, we already know it. Can we extract the pins? Well, not from the HSM, but we can see them on the wire. We can see them encrypted in the logs. But we know what the key is now. We just take them on our own computer, open SSL, and just decrypt this using the null key. Yes? You agree? Feasible? Maybe. It is. It is. So, another attack. HSMs have got multiple keys for different reasons. They have local master keys under which they encrypt everything else. They have terminal master keys, which are the master keys deployed on the ATMs, which speak to the central location. Of course, they need to know the keys of the ATMs because they talk to the ATMs. They have pin derivation keys, they have terminal communication keys. The difference between a terminal master key and a terminal communication key is the following. Both of them are ATM keys. However, the ATM uses the communication key to encrypt the pins and the master key to exchange communication keys. There is a keying hierarchy here. Let's see what might happen. And this is as bad as it gets. I promise you, it's not going to get worse than that. This is called the two-time attack. And it's called the two-time attack because we're encrypting the same key twice, or the same quantity twice. Only we are telling the HSM to use one type of key instead of another. So, what is the primary, what is the pin? The pin is your card number encrypted under the pin derivation key. If we can take your card number and convince the HSM that this is a terminal communication key and encrypted under, the terminal master key, then what we're going to get out is this particular value, which is of no particular use to us at this point because it's something we already know. The second step is to take this encrypted card number, which is now considered to be a terminal communication key, and we encrypt it under the master key of the terminal to send it to it. However, instead of supplying the master key of the terminal, we supply the pin derivation key. And what happens then? We ask for this transaction to take place. We're going to get back a value. The value we are going to get back, funnily enough, and you can take a look at your own time and confirm that it's true, is the pin itself. And that's as hard as it gets. It's not going to get any harder than this. It's all downhill from now, both in terms of easiness, also in terms of security. Meet in the middle. every HSM stores an awful lot of different keys. Imagine a bank's HSM, and that bank might have 100, 1,000 ATMs. There are 1,000 keys stored there. There might be other types of keys. Now, what can we do? We just take one test pattern, whatever it is, one quantity that we know. We encrypt it under all the different HSM keys, and we note the results. Does that help us find the key? No, not yet. But then we start brute forcing. We take a quantity that we suspect might be a key, and we encrypt that same known quantity. And then we make a lookup. Does that really speed up the process? It does, because the expensive transaction in terms of time is the encryption, not the comparison, especially if you hash the keys. So for each encryption, you don't have one true or false against one key. You have one true or false for each one of the stored keys. So you might speed the brute forcing attack by 100, by 1,000, by 10,000, depending on how many keys are stored inside the HSM. Decimalization attack. We said that the pins are converted from hexadecimal to decimal using a conversion decimalization table. Most of the HSMs, most of the standardized HSMs APIs, allow the decimalization table to be an input to the pin verify transaction. Now, if we manage to alter this table, and it's very easy because we specified, we give it as an input to the function, then an awful lot of information is leaked, and we will see how. The attack strategy is to repeatedly change one entry in the decimalization table and observe the results. And the results are, in phase one, we identify individual pin digits, and in phase two, we identify the position of those digits in the victim's pin. So this is the normal operation that we saw before. Let's see it with some numbers. So we start with the PAN, which is at the top, and the encryption key, and we get out a ciphertext, which is E481. Well, E stands for 4, 4 stands for 4, 8 stands for 8, and 1 stands for 1. So the digit after digit replacement, this is the output, 4481. We take also the offset, 2118. Well, if we do modulo 10 addition, this is the pin, and whatever comes in from the ATM, we decrypt it, we check whether they are the same, and we come up with a yes or no. Now, the encrypted pin block must be known to the attacker. How can it be known to the attacker? They can either sniff the network, or they can compromise switches, of which we're going to discuss more later. And for simplicity's sake, let's assume in the next examples that the offset is 0. The client has not yet changed his pin. So the normal flow, we start with the PAN at the top and the encryption key. This gets decrypted, digit replacement. Now this time the pin is 4481 because the offset was 0. This gets encrypted, and we get a yes. Now, what do? We go here, and we submit a different decimalization table. A table that the hexadecimal digit of 0 gets suddenly replaced, rather than with 0, this time with 1. So, if you follow this, you will see that because there is no 1, no 0 in our hexadecimal string, E481 contains no 0, the result of the digit replacement is 4481, which is exactly the same. So it says, yes, it will go through. Conclusion, the PIN does not contain a 0. Now, what happens if we go and we change hexadecimal digit 1 to correspond to a 0? Now, this time, E481 gets replaced to 4480. Now, if we add all these zeros to this, we get 4480. The trial, this is the trial pin, 4481. They're not the same. So what do we get out as a result? The pin contains the digit 1. But now, we don't know where. We know it contains the digit 1, but we don't know in which position. So now we pass. Of course, we do this many times, up to 16 times, to find out the different digits, yes? But once we find out all 4 digits, we then go to find out which position they're in. And for that, we keep the decimalization table constant, and we start playing with the offset. So now, 4480, changing the offset with the first digit to be 1 rather than 0, will lead us to a 5480, which is not the same. So we know now that digit 1 is not in the first position because we altered the first position of the offset. Same attack, we move we change the digit, the second digit of the offset. Digit 1 is not the pin second digit. It's not the third digit, but hey, we got it at the 4th time. The 4th attempt. When we modify the last digit of the offset, what do we get? 4481. And now we know that 1 is the 4th digit of the pin. How long does it take? If we know the offset, anywhere between 1 to 20 seconds. Provided you know how to write a for loop. Otherwise, it might take slightly longer. With an unknown offset, if you're lucky 10, if you're not lucky, up to 1,000, 1,100 seconds, which is not a lot. That's the final attack. It's called the translation attack. And as we said, banks need to interchange information. And because they need to interchange information, they need to encrypt pins that they acquire to send to the issuing bank. So there are some nodes, some HSMs, sitting on the edge of keying zones that receive things encrypted with the bank's communication keys, and they translate them, they decrypt, and then re-encrypt it under the key they share with another keying zone. However, because not everything in this world has been standardized, I was having problems with my power supply. I had a European connector. Apart from doing this translation by decrypting and re-encrypting, the other financial institution might be using a different ISO pin block format than the one the organization uses. So the translation function always gives you the capability of switching ISO format. So if my bank is using ISO 3 and the other bank uses ISO 0, the keying change, the translation function, will not only need to decrypt the pin and re-encrypt it with the other bank's key, it will only need to reformat the pin block. So how do we prepare for this attack? We just need to pre-compute a table of 10,000 encrypted pin blocks using ISO 0 format. The ISO 0 format, if you remember, uses a constant filler after the pin, which is all Fs, and the client's card number. When we do that pre-computation, we use a known card number. Let's assume it's all zeros. We create a table whereby the nth entry corresponds to the nth number between 0000 and 9999. So, for each and every encrypted PIN block that we might see, we might receive, what do? We take it, we convert it to ISO 1. If you remember, ISO 1 is a format which uses the PIN and then some, it does not use the account number, it just uses the PIN and the filler. So by converting the PIN block into ISO 0, we then break the relationship of the PIN with the card number. Because ISO 0 doesn't take into consideration the card, it's only the PIN and the filler. So we break that relationship. And then we re-encrypt under ISO 0. Now, if you ask an HSM to convert ISO 1 that has no card number information to ISO 0, which has card information, it will ask you for the card number. So we take something that has information of the original card, we break that relationship, we make the HSM forget about that card number, give us back an encrypted value of the PIN only, and then we turn this into an ISO 0 PIN block with a card number that we know. Which card number? The same one we used for the precomputation of the 10,000 entities. And then it's just a matter of a simple lookup. You just take a look at the table and you say, oh, which one is this? It's entry 9,187. Guess what? The PIN is 9,187. This is a rhetorical question. I would be thrilled if you had digested the entire presentation and you could answer this question, but maybe you have not. So that's for something, a question to take home if you ever take a look at this presentation again, and if you find the answer, great, answers on a postcard. What happens if we combine the translation attack with the XOR to null attack, especially XOR to null attack in a keying zone, in a place where we translate pins? Conventional IT attacks. We saw the PIN attacks. Now let's see what can happen inside a bank's network. ATMs have moved from being special purpose black box machines to still special purpose Windows machines. This was brought on by the need for new services, for processing speed, for system integration, for reduction of cost and ownership, and it has led, of course, to the adoption of many mainstream technologies like TCP/IP and Windows. Before it used to be X25. This has managed to change dramatically the threat model. Few things that can go wrong. You don't want to see this in your bank's ATM, would you? Would you want to see this on top of an ATM? I don't think so. These are pictures taken by my colleagues at ATMs. They were thinking of putting the card in. They said, no, that's not a good idea. I'll go somewhere else. So traditionally, a TCP/IP ATM network more or less looks like this. You've got here the central location, the bank's data center with the host, usually HP non-stops with some HSM attached to them. Then the various networks. Here you've got the branch, here you've got the ATM, which surprisingly enough connects back home through the branch router. So ATM traffic is actually goes through the branch router. It's not a dedicated device. So if somebody's IT savvy in the branch, he can collect encrypted PIN blocks. And of course there are some remote ATMs which either get connected through branches or directly they speak back to HQ. So what can go wrong? You've got an attacker, he's sending a nice email to some of the bank employees. Here's a nice game, check it out. Here's a nice article I wrote. They managed to compromise a workstation within the bank's secure perimeter. That's not rocket science. Undetectable backdoors and reverse tunnel technologies have been known for the last 9 or 10 years. Obtain full access on somebody internal, and then you obtain also network access. You try to expand that, you do your network discovery, information mapping, analyze information, then you target the ATM. And from the ATM, from that same computer, you start doing attacks on the ATM itself. Something that used to be the privilege, these attacks used to be the privilege of people who were sitting here, suddenly have gone out here. Especially when we talk about interbanking switches. These huge boxes which aggregate all the transactions and they distribute them around. Some of them are the responsibility of service providers, not the banks themselves. So, would you be surprised to know that the majority of those switches have admin and management interfaces on the internet? No. Other types of attacks which are no longer that effective, but we still see them taking place. Normally, when you go to an ATM and you type your PIN, there are two different ways of encrypting it. One is to use the native operating system capabilities or the ATM application capabilities to encrypt the PIN and send it on its merry way. Another way, much more secure and lately made compulsory, is to make the encryption on the PIN pad itself. The PIN entry device, the PIN pad, has to conform to special characteristics and do the encryption there. The reason being, if you're using the native operating system or the application, the ATM controlling application characteristics, then the PIN pad becomes yet another keyboard. There's nothing prohibiting somebody from deploying a keylogger to capture pins before they get encrypted. And it's not only pins, it's only card numbers. It's also card numbers. So, some final thoughts before we close this. The security of the online PIN transaction scheme, framework, and the protocols themselves, unfortunately, leaves a lot to be desired. We could go on ad infinitum to discuss whose fault this is, but it is a combination of factors that has led us to this particular situation. Backwards compatibility, lack of standardization, and many others. Also the fact that when these devices and these protocols were designed, they were supposed to be black holes, black boxes. Security through obscurity used to work fine in the 80s. Doesn't work anymore. And also security engineering and research about the formal verification of security protocols was really non-existent outside rocket science and embedded systems and air traffic control. These were, in the 80s and the early 90s, these were the areas that were using, Z or communicating serial protocols or ban logic to formally prove the claims of any protocol. However, nowadays, things have improved. Now that means that we have to revisit all this. The attacks, four of them we described today against PINs, used to be the realm of academia. Some of them were observed and documented in papers by some very bright individuals. Some of them were found by specialized software, designed and developed in the last 4 to 5 years. However, these attacks are no longer in the realm of academia. They take place as we speak, and it's surprising to see that the reaction of the perpetrators being so fast. There are ATM API attacks announced in cryptographic conferences in March, and then you see some malware implementing this and being deployed on banks' infrastructures after 6 to 8 weeks. So obviously, we are going to be seeing a lot more of those attacks in the future. It's pointless to go and try to hack the ATM when you can get cards and pins by the bulk load. A word of thought, just the final one. When you talk to a bank, they're right. They are going to say, we use industry best practices. We're a secure shop. We design, we develop, we employ, we enforce strong physical security policies and procedures. So we're safe. That's true. But why would I try to attack the safe bank? Why wouldn't I try to attack a bank that does not employ all these security procedures and all this strong physical security? After all, the secure banks' card numbers and pins travel through insecure bank networks of other banks. I travel abroad. Regardless of how much I trust my bank and do secure transactions in my country of residence, the moment I go to a different bank, I'm at their mercy. Is it safe to assume that all the banks in all the world will implement a high watermark security? No, not really. So attackers are bound to attack the weakest link. Also, why would the banks invest in purchasing extremely expensive, tamper-resistant security modules when the first line of defense is physical security and policies and procedures? That's the final thought. Ladies and gentlemen, thank you very much for your patience, your time. I hope you enjoyed this as much as I'm enjoying the conference. Do you have any questions? Please.
Normally, the ATM and the bank network, they are separated, right? Normally. Okay, this is the first question. And then the second question is, because your offset normally stored in mainframe database, mainframe, and then the application side actually has some other mitigation step, like you have try 3 times, then you block your account. So how do you do that attack if they have such mitigations in place?
Okay. First question is, how segregated is the network, the ATM network from the internal banking network? In a secure bank, a lot. In an insecure bank, at all. I was doing an on-site assessment on a very large bank, and it was that particular country's largest card issuer. They had an impending audit by one of the payment card brands, so they needed to make sure that the security was up to scratch. So we went to the card processing center, extremely strong physical security, biometrics, the lot. In order to go and check the HSMs, you had to go through hell. The only thing they didn't ask was DNA samples. I took a look at everything and it was really watertight. Then we went back to headquarters in a different city and I said, I forgot to ask you to show me how you do this. Oh, I can't believe I had been so careless. But, we must reschedule another meeting because I need to see how you guys do this on the HSM. I said, don't worry, I can show you. So, we've got a test ATM here, HSM here. No, I'll show you. Telnet. So, how segregated is an ATM network from the core IT network? As segregated as a bank wants it to be. Secondly, you're very right. The cards, the pins, you cannot do tries indefinitely. You cannot try 100,000 different pins. For starters, there are only 10,000. But all these attacks that we described, they're being performed on the HSM, not on the ATM. You have the encrypted pin block. The client has already put in his pin. What you're doing is you are manipulating the HSM to reveal somebody else's correct pin. You don't do trial and error. So the attacks will work fine because you have the HSM. You have you have programmatic logical access to it. Any other questions? Please.
I want to ask about the HSM and the main OS. Is it HSM sort of module, like PCI module in the PC of ATM machine?
Okay. They can be both. Normally, 90% of the banks, a few years ago, they used to use some RACAL HSMs. RACAL, R-A-C-A-L. RACAL has been bought by Thales. Now they're called the Thales boxes. It's the RG X000 series, so you have RG 7000, 8000, whatever. Now they are rebranded. They are rack mounted. They're not inside a host. There is either there can be either network communication or direct attachment.
Means one PC and one HSM.
The HSM does not speak to a PC. It speaks to the host that runs the ATM controlling application, which normally, traditionally, for fault tolerance purposes, they used to be Tandem boxes. Then Tandem was bought by Compaq. They changed the name, and then Compaq was bought by HP. Now they're called HP non-stops, but everybody calls them the Tandem. Okay, non-stop. Well, we have some stories for that, but that's going to be another presentation another day. Please.
Just holistically, what do you think should be done in this industry or in banks individually to maybe make the system more secure, or at least make the industry more standardized? What do you think should be done?
In the short term, there aren't many things that can be done. The question was what can be done in order to raise the overall level of security in the short term. And so, you didn't say in the short term. No. Okay. In the short term, there's not much that can be done. It's not feasible to ask all the banks, even if we had an immediate solution for the protocols. We designed overnight secure protocols. It's not feasible to go to every single bank, every single service provider, financial transaction processing system provider, and ask them to overhaul their infrastructure and change it. It's not going to work. In the long run, or in the medium term, this is what we should be doing. Redesigning the protocols from scratch. Making sure that authorization is right on the API. So the same transaction cannot be executed, the XOR null attack, for example. Why would the same programmer submit two different key parts when the reason you have the key parts is for segregation? So this is the medium term. In the short term, there's no solution. There's no solution. So either the banks which are lagging behind in terms of security, they have to, run a tighter ship, or we're doomed. Well, we're doomed if we use their networks. So, no. I believe that in the short and somewhat medium term, we will see more and more and more malware coming out and targeting banks. And why not, few viruses also. What's the chance of, the major antivirus vendors detecting pin-stealing viruses if they don't exhibit any type of behavior on a normal user's PC, but they only do things like that on an HSM. So I don't think there is a short-term solution, I'm afraid. Any other questions? Thank you very much for your time.